Okay, so welcome back to physics. This is the second part of the unit 3. So you've been through different types of work and energy, and if you remember, they're being measured in joules. So we've been dealing with kinetic energy, potential energy, and work, and the conservation of energy. We're now moving to the second part. We're still talking about energy, but this time we're talking about the heat energy. Okay, so you should have watched the other video from Professor Dave already, so you should know what specific heat capacity is. So I'm still going to highlight this term because this is something that we will be using quite a bit. So specific heat capacity has a lowercase c as a symbol. It's basically telling you how much energy, if I have an object, whatever it is, whether it's liquid or solid, if I have something and I have 1 kilogram of it, and whatever temperature it is, either if I want to increase it or decrease it, if I want to change the temperature by 1 degree Celsius, basically the amount of heat that it will require. The symbol for heat is Q. So specific heat capacity is whatever the object is. If I have 1 kilogram of the object, but if I want to change the temperature by 1 degree Celsius, how much heat will it require? If you think about something that are metals, like say your aluminum at home, if I have 1 kilogram of aluminum at home, because it's a good conductor, you see how you don't need a lot of energy to get that going. But then say, for example, if it's water, okay? How much heat does it take for 1 kilogram to heat up? It's going to be different. If you go to your textbook, if I can find the textbook, if you go to the textbook, which is attached into your file, and you can actually take a look at the specific heat capacity for the different things. I don't know if I have a pen here. No, I can't. Okay, so take a look at this chart right here. It is the specific heat capacity. If you take a look at the first one, which is water, water takes 4.18 times 10 to the 3, so 4,180 joules to heat 1 kilogram of water by 1 degree Celsius. But if you look down the sheet, say aluminum, you require 920 joules to do that. So basically, the better the conductor, the less heat it will require to change the temperature by 1 degree Celsius. And that's what specific heat capacity is. Okay, so commonly used number is water. Okay, but you can always just look it up from the chart from there. So if I say water, it is 4,180 joules per kilogram degree Celsius. Does the unit make sense to you? Raise for 1 kilogram mass to change it by 1 degree Celsius. That's how much it takes, how much heat it takes. Okay, and then they tell you like, oh, it's about 2,000 for vegetable oil, and that's what it means. Okay, and then the equation is Q equals mc delta T. So let's just talk about the unit. Okay, so Q is heat energy, is measured in joules. So this is heat energy. That's a symbol for it. So just like EK is kinetic energy, Q is heat energy. Mass is probably your most tricky thing, is your SI unit. I still find that people get confused with the SI unit for mass. It is in kilogram. Okay. And delta T, we always can have, whenever we do anything in delta, means the change. It's always the final temperature minus the initial temperature. Okay, and then the last one we already talked about it is your C. What's the name for it again? You need to know the term, because basically that's the only tricky thing, is you need to know what the question is asking or what they give you. So C is the specific heat capacity, and is measured in the unit how much energy in joules it takes to change 1 kilogram by 1 degree Celsius. And that's why this is in kilogram per joule per kilogram degree Celsius. Okay, so the next page is just saying what is change in temperature. Okay, so we're going to do an example first. So I'm going to ask you to flip to let's find example number 1. The question says, when 200 milliliters of water is heated from 15 degrees Celsius to 40, how much thermal energy, which is heat, is absorbed by the water? They tell you the density of water is 1. So a little rule of thumb, if you want to write this at the side, if you want to ever because its density is mass over volume, you learned that in grade 9. So basically 1 milliliters is basically 1 grams, and 1 liter is 1 kilogram. I'm not going to bother showing the full work, but I do need you to know how to do the conversion. Okay, so in this case, I still wanted to say the mass. Instead of 200 milliliters, if I look here, 1 milliliters is 1 gram. So that means this one is actually 200 grams of water. And don't forget, we need our unit to be in SI unit, which is kilogram. So divided by 1,000. So this becomes 0.200 kilogram of water. Water is the substance. If you are given water, in here it didn't give you, but if they give you the substance, you can always go back to the chart in the textbook. And I know water is 4.18 times 10 to the 3. You have the textbook, right? So just take a look at it, and we always will give you the value. I wouldn't expect you to memorize what they are. So 4.18 times 10 to the 3 joules per kilogram degree Celsius, because they gave you water. You look it up from the chart. Okay, and then they tell you that the initial temperature, which is your T1, is 15. And then your final temperature, which is your T2, is 40 degrees Celsius. How much energy is absorbed? So that is Q. The equation for heat rise and drop is Q equals MC delta T. I'm looking for Q. So M, I found that this is 0.2. The C is 4.18 times 10 to the 3. Delta T is T2, so your final temperature, which is 40, minus your initial temperature, which is 15. Punch it in your calculator. So just be careful of the brackets, right? When you solve for anything in the bracket, make sure you do that one first. So the answer I got is 209. So this is what I got, 20900. And then take a look at SIGDIGs. I have 2 SIGDIGs is what we're going to be using. I know we didn't really use it in the calculations, but you did, because in order to do this, you did the calculations already. So 2 SIGDIG is what we're using. So 2.1 times 10 to the 1, 2, 3, 4. So times 10 to the 4 joules. Okay, question 2. Okay, copper. An empty copper pot. They already gave you the specific heat capacity. The pot has a mass of 1.2 kilogram in proper SI unit already, and it is at a temperature of 130 degrees. If it was to cool to the room temperature of 20 mod, how much thermal energy? So C is 3.8 times 10 to the 2. Notice it's a lot smaller than water because it's a good conductor, meaning it doesn't require as much heat to raise or drop the temperature. So 1.2 kilogram is the mass. The initial temperature is 130. And the final temperature is 21. Sorry, my kids are making pizza. Find what is the thermal energy, Q. So Q equals MC delta T. M is 1.2. C is 380. Is that okay that I do the conversion right away? I'm not going to punch it in as 3.8 times 10 to the 2. And then I have delta T, which is T2, 21, minus T1, which is 130. Punch it in the calculator. Bless you. Okay, so I got a number of something like this. Is that what you got? So, SIGDIGs, 3.8, meaning it has 2 SIGDIGs. So I'm going to do 2 SIGDIG as the answer. So I need to round it to 2 SIGDIGs. So I can't just say 50. Like if I were to do 2 SIGDIGs, like these are the 2 that I'm keeping. I'm rounding. I can't, because it's a 7, I have to round up. I can't say 5 like 50,000. That would be 1 sig. So I'm going to have to put it as negative 5.0 times 10 to the 4 joules. And the negative makes sense because you're losing the heat on the copper pot so that it goes to the surrounding. So the therefore statement would be, therefore 5.0 times 10 to the 4 joules of energy is released to the surrounding. That's why it's a negative value. So the negative value means that you actually lost heat. Okay, continuing on for question number 3. A block of iron, it tells you C is 450. Start off at the temperature of 22. It is heated to 100 by placing it in boiling water. The quantities of thermal energy requires for this temperature to change to occur is 4.91 times 10 to the 5 joules. Calculate the mass. So write out my given. Let's do it. Okay, so it tells me iron has 450 joules per kilogram degree Celsius. The initial temperature is 22, so that's my T1. It's heated to 100 by placing it in the boiling water. So they dumped it in water, they keep boiling it, so the water and the iron now has the same temperature at 100, and they tell you the heat is 4.91 times 10 to the 5. They would like you to calculate mass. So Q is mc delta T. So 4.91 times 10 to the 5 is equals to M, which is what you're looking for. C is 450. T2 is 100 minus 22. Okay. This is one equation with one unknown. I know you're going to say this is so easy. I'm going to ask you to pause the video. I need you to do the math and then check your answers. I find that sometimes people have issues when I have things like that at the back. Like it looks like a really straightforward rearranging equation. Please punch it in the calculator and get one for me. What'd you get? Okay, the answer should be, I have 2 sig digs again because I have the 4.5. So 2 sig digs is what I'm putting down. And the answer is 14 SI units, so it's in kilogram. Did you punch it in? Did you try it? If you can't, do it in one step. So when I punch it in a calculator, I would punch 4.91 times 10 to the 5, divide 450, divide, and then I would put this in bracket, 100 minus 22, close bracket, equals. Okay, if you can't do it in one step like that, figure out what's on the right hand side and then divide both sides by that. Okay, so just be careful with your math. So now that we know how to use the equation Q equals the mc delta T, we're going to move on to the second part of the lesson, which is called the principle of thermal energy exchange. Basically, very similar to the conservation of energy. Okay, so this is relating to the conservation of energy, and these types of questions always involve 2 objects. For example, if I have a bucket of water, okay, so whatever mass it is, which is colder, okay, so it started off at whatever the initial temperature is, and then at the same time, we're saying that we have this block that is really, really hot, whatever the initial temperature is. So I'm going to call this T1 for the red, and I'm going to call this T1 for the hot water. And whatever temperature it started out with, what happened is if I actually add these 2 together, and if I now decided to dump this block into the water, what is going to happen? Does it make sense that there will be some sort of transfer of energy from one object to another? And if you understand that with common sense, does it make sense that I'm going to tell you that the energy is going to come from the block into the water? So what that means is, what this has experienced is the red would have experienced some loss of energy, right? Some energy is now being lost. And then while at the same time, the water the colder one would have experienced some sort of Q gain in order for, like, when I dump the two together, that's what happened. Okay, so the first thing you need to understand is the amount of heat that is lost have to be the same as the amount of heat that is gained. And that's what it means by the principle of thermal energy. If we read the caption at the top, when thermal energy is transferred from a warmer object to a colder object, the amount of thermal energy released by the warmer object is equals to the amount of energy that is absorbed by the colder object. That just makes sense, right? The energy just got transferred, and until which point will it stop? The key thing is until they both have the same temperature. Okay, so the red block will keep losing the heat, the water will keep absorbing the heat. It will get to the point when the final temperature of both objects is the same for both of the object, then your thermal energy will stop transferring because there's no more transfer of energy. They're now having the same thermal energy. Okay, so the equation that we use here is Q release plus Q absorb equals to 0. I like to write it another way, so I'm just gonna get another page. This is how I would write it. Okay, so when I do these kind of work, I will always do like kind of the hot object and then kind of the cold object in two different color or in two different column. And the equation that I would use is the hot object will lose, right? So we will write the Q loss. So I'm just going to change the color back to red. So Q lost by the hot object, adding the heat that is gained by the cold object. Theoretically, according to the conservation of energy, it should equals to 0, right? Because remember the examples we were doing, when we're losing energy, it actually becomes a negative number. So like this, with the Q loss should be a negative number, and then the Q gain is positive, and I add the two together, they should cancel and equals to 0. So if I were to expand this equation, I know that the equation for Q is mc delta T. So if I work them out separately, so I could say that this is equals to mc, so mc delta T adding mc delta T equals to 0. Some people like to put it on the other side and make it negative. It's up to you when you want to rearrange it. And then don't forget that sometimes, depending on what the question is, sometimes they'll tell you, oh, it raised the temperature by 3 degrees. They gave you delta T. But if they give you like it started at 12 degrees, it is now 25, sometimes you might need to expand this equation a little bit more depending on the situation. Okay? Okay, so that's the equation. So the commonly used one is this one, and you need to know your mc delta T anyway from before, and this is the expanded version depending on what you need. Okay, so let's try out the example. Okay, so let's carefully read the question first. A 60 grams of metal is heated to 100 degrees Celsius before placing in 200 milliliters of water with an initial temperature of 10. The metal-water combination reached a final temperature of 15.6. This one is actually for both, right? So 15.6 is actually for both objects because the water and the metal both becomes 15.6. Okay, I'm going to start out with two lists. Okay, I'm going to say one list is called the metal. The metal is the one that is going to go through the heat loss because it was hotter to start off with and then it'll cool down. So I know that the mass is 60 grams. So we don't like that. We need it in kilogram. So divided by 1,000. Hopefully you remember how to convert. Okay, it was at a temperature of 100 and then it became 15.6. They're asking for, I didn't finish reading the question, the specific heat capacity of the metal. So they would like you to find C for the metal. And then I'm going to change color, start another list. It's important that you keep the list separate and very clear so that you don't make a mistake, right? Like, and plug, the wrong value into the wrong side. Okay, so water, I'm going to make a little note. This is the one that is going to go through the heat gain. I have 200 milliliters, meaning 200 grams. Remember how we said that because the density of water is 1. So this is 200 grams. And so 0.2 kilogram is what the mass is in SI unit. And it tells you it's water. So I already have that from the textbook. Remember how we said we can look it up when they give you the value, right? So water, 4.18 times 10 to the 3 joules per kilogram degree Celsius. I would never expect you to memorize that, as I said before. And it tells you that the initial temperature is 10 and the final temperature is 15.6. So key thing, the combination means they both have the same, okay? All right, so let's start writing our equation. So heat loss plus heat gain is equals to 0. I'm going to write my value, MC delta T, adding MC delta T is equals to 0. The reason I say that is because I know Q is MC delta T. That's the equation that we're given. So I'm just expanding it out. Now I'm going to plug in my values. M. So for the list that's on the left-hand side, MC is what I'm looking for. So that's my unknown. Delta T is 15.6 minus 100. So T2 minus T1, so 15.6 is your final. And adding, now doing the blue part, which is the water part, M is 0.2, C is 4180, delta T is T2, 15.6, minus T1, which is 10, all equals to 0. Now you're punching things in the calculator. I'm going to show step by step. So I punch everything for the red part. The value worked out to be negative 5.064 times the C. I just go 0.06 times bracket 15.6 minus 100. And then I'm going to work on the blue part. So punch everything in the calculator. So 0.2 times 4180 times bracket 15.6 minus 10, 4681.6 equals to 0. I'm going to bring the blue over to the other side. And now it becomes a minus. So I'm going to keep the red. And I'm going to move the blue over to the other side by subtracting. So minus 4681.6. Then I'm going to divide both sides by the 5.064, the negative of it. So C should be a positive value, which makes sense. And it worked out to be 924.48. Check my SIGDIGS. This question has 3 significant digits, so 924. What's the unit for specific heat? Yeah. Joules per kilogram degree Celsius. Yes. All right. I do have a side story. I like telling story. I haven't been telling a lot of stories lately. Okay. I'm going to show you a video. This is what we're doing. Okay. We are making pizza at home. So what happened is we didn't have a thermometer. And the first time we were making pizza, we were told that you need 35 degrees Celsius lukewarm water for the yeast to grow. And it was the first time that Nathan ever made pizza. And we were doubting him that because I tried making sourdough or something like that, and then it didn't work. And so I was doubting him. I was thinking it wouldn't work. So I'm like, okay, fine, give it a try. We'll do that. All right. Oh, first time you see my kids. Yes. So then I thought, okay, I will give it a try. So ended up, I actually used the heat exchange for a specific heat capacity. You might not believe it. We actually had to work it out. So what we had to do, I'm not going to go through the full thing, but we have a machine at home that is like, I don't know what it's called. It's like it's plugged into the wall as water, and it actually keeps the water at a temperature of 95 degrees Celsius. And then we also have water jug at home that is room temperature at T1. So both of them are T1. And it worked out to be, it was like a room temperature, so I assume it to be a 25 degrees Celsius. And then we need to figure out how much of the hot water and the cold water we need so that we can actually create a water temperature of 35 degrees Celsius by mixing these two together with the known quantities and our piece of work. So I'm going to leave this to you to figure out the ratio. If I want 100 milliliters of the hot water ratio to the cold water, how much do I need to mix it together so that I can actually get it to work? We actually did the math, and we found we mixed the water together, and it actually worked. Okay, so I just want to tell you there are actually useful things with physics. All right, last example is example number 5. This is the typical test question. Okay, oh no, actually it's not the typical. This is actually not the hard one. I actually put a typical test question on your homework question, but we'll get to that in a minute. Okay, sample of iron. Specific heat capacity is 450, heated to 80, and placed in 100 milliliters of water at 20. Final temperature of the mixture is 22. What is the mass of the iron? Okay, so to list again. I like to do the hot one in red. So iron is the one that is going to go through the heat lost. And iron has a specific heat capacity of 450. And it is heated to 80. And it's placed in 100 milliliters of water. Oh, sorry, I'm just going to finish up. The final temperature is 22 for iron as well as for water, right? So water is the part that is going through the heat gain. And water, the mass of the water is 100 grams or 0.1 kilogram of water. And the initial temperature of water is 20. And final temperature of water is 22. And since I know this is water, I check my chart. I know my given as well. And then they're asking you, what is the mass? Okay, so heat loss adding heat gain is equals to 0. You always start off with this equation. This is almost like your beginning equation. Because of conservation of energy, because of the principle of thermal exchange, I know that the heat gain and heat loss have to be the same between the two objects. And then now I'm going to start subbing things in. I know Q is mc delta T, adding mc delta T. If you get it and you don't need to change color, be my guest. I'm still going to do it one more time just to make sure everybody's on board where things comes from. M is what I'm looking for. I look at the list that is red. Okay, I'm being consistent one side compared to the other. MC is 450. T2 minus T1. Adding MC delta T is T2 minus T1, all equals to 0. So negative 26100 M, adding 836 equal 0. Okay, bring the 836 to the other side. divide both sides by 26,100. I end up with a positive value of, I don't know, is this right? 0.032. Double check for me. I will need 2 signics. Okay. All right, this is the last question. I challenge you to pause my video, do this all on your own, and check your answers. You have to apply your math. You do your proper expanding. If there's a binomial and a bracket and all those stuff, collect your like terms and be very careful with your units. So pause the video, do it, and then I'm gonna do it. Okay. All right. So 200 grams of silver. Specific heat is 240. Heated to 90. The hot silver is then placed in 300 grams of ethyl alcohol, 2460. Specific heat with the initial temperature. You need to find the final temperature of the silver alcohol mixture. Keeping in mind the T2 is the same for the two sides. Okay. All right. So silver. Okay. So silver is the one that's going through the heat lost. Silver has a mass of 0.2 kilogram with a specific heat of 240 joules kilogram degree Celsius. It was heated to 90. I do not know what the T2 is. That's what I'm looking for. Then the alcohol. Okay, this is the heat gain. And I have 300 grams, so 0.3 kilogram. Specific heat is 2460. I just expand out the scientific notation. It has an initial temperature of 5, and they're asking for what is the final temperature. Start out with the same equation. Q loss adding Q gain is equal to 0. Since I know Q is MC delta T, okay, so each Q is now replaced by MC delta T. I'm going to plug in my value. So MC, 240. T2, I don't know what it is. T1 is 90. Adding M C T2 minus 5 equals 0. Okay, so the first thing I'm going to do is I'm going to calculate out what this is point first. So 48 is T2 minus 90, adding. Then I'm going to do the same thing. I'm going to multiply this out. 738 T2 minus 5 equals 0. So all I'm doing is just multiplying them out. And then notice that I have a binomial, meaning I need to take my term on the outside and I'm going to multiply in by expanding. So I'm going to take 48 times T2. 48 times 90. So 48 T2. Be careful of your sign. It is a negative. So I have minus 4320. Adding. I'll do the same thing. There is a binomial, meaning I need to expand this out. So 738 T2, and then take your 738 and times it by your minus 5. So 3690 equals to 0. The next thing you need to do is collect your like terms. Okay, so T2 and T2 are your like terms. So I have 48 plus 738. And then at the same time, I have a number and a number. So I'm going to move them over to the right-hand side. I'm going to move all the numbers to the right-hand side. I'm going to keep the T2 on the left-hand side. So 48 T2 adding 738 T2, it equals to 3690. I move them to the other side. They become positive. So collect the like terms and add them up. So all I did is add up the like terms. So 786 T2 is equal to 80, 10. Now divide both sides by 786. Your T2 worked out to be 10.19. Check your sig digs. So 2 sig digs is what I want. Typical test question. You know you're going to get this. Problem set will have it. Your homework will have it. It's not hard. The key thing of your success criteria, if we take a look at it, is, of course, you need to start off with the concept. I'm going to make this the purple color maybe. Okay, so we're going to start off with the equation for principle of thermal exchange. There will be 1 mark for given, knowing that Q is MC delta T, and then 2 more marks for solving them. So this is a 4-mark question. It's not too bad. Okay, so try them out.